Welcome. Today I want to share with you how to accelerate polarization via alphabet extension. The subject of this talk is Polar code. Polar code is a young error-correcting code that achieves channel capacity and is recently adapted into the 5G communication standard. Today, we'll be focusing on the capacity achieving property. For an error-correcting code to achieve channel capacity, the code rate must increase and converge to the capacity as the block length grows to infinity. This begs the following question. How fast does Polar code achieve capacity? As it turns out, if you take the gap between capacity and code rate and raise it to the power of negative mu, where mu is a magic number, then the result will be approximately the block length. This magic number, mu, is called the scaling exponent, and there are many works that aim to figure out the exact value of mu. I listed some of them just to show you how important mu is. There are as many works that aim to improve mu. The popular technique here is to increase the size of the so-called kernel matrix. We, however, take a different approach. Before we dive into our new approach, let's review binary erasure channel. A binary erasure channel is a channel with input 0 or 1 and output 0 or 1 or question mark. A 0 can remain 0 or become a question mark. A 1 can remain 1 or become a question mark. The probability that a bit becomes a question mark is called the erasure probability. And here is how to construct Polar code over BEC. Imagine that a BEC with erasure probability 1 minus x is a wire with connection probability x. The serial concatenation of two BECs has connection probability x squared. The parallel combination of two BECs has connection probability 1 minus x squared. One then applies serial concatenation and parallel combination recursively to generate more complicated circuits. Here is a bigger picture that shows 5 generations of the circuits. Suppose that each small wire has connection probability 1/2. We can sort these circuits using their connection probabilities. As you can see, most circuits move to the either side of the screen. This is called polarization. A user of Polar code will use circuits with high connection probabilities to transmit information. To measure the extent of polarization, we assign each circuit a score. The lower the score, the closer the circuit is to the sides of the screen. Therefore, by adding the score of all circuits together, we can obtain an overall measurement of polarization. This sum is closely related to the scaling exponent of Polar code. To see the relation, suppose that the score function satisfies that the score of the parallel plus the score of the serial divided by twice the score of the original wire is 2 to the negative 1 over mu. We can visualize this quotient as follows. Pick a point on the score curve, pinpoint the serial point, pinpoint the parallel point, and then take the midpoint. Then the quotient is the ratio between the heights of the green and blue dots. That will imply that the scaling exponent of Polar code is mu. This approach, using the score function, is the standard tool to study Polar code, and we will also follow this path. Now allow me to introduce tetrahedral erasure channel. The input of the TEC is a pair of bits. The output of a TEC is a triple of bits, but sometimes only U survives the erasure. Sometimes only U plus V survives the erasure. Sometimes only V survives the erasure. And the worst of all, sometimes nothing survives. So where is the tetrahedron, you ask? Well, here it is. We let TEC PQRST be a tetrahedral erasure channel where each lower letter corresponds to the probability of an erasure pattern. Next, we want to generalize serial concatenation and parallel combination to tetrahedral erasure channel. What you see here is the naive approach. We then make a little tweak to incorporate finite field arithmetic. You can barely see any changes, but that is what it takes to improve Polar code. Following that, we define some properties of TEC that will be used in the proof. See the paper for more details. Here is a cartoon that shows the relation among what we just defined. And here is a proof sketch. Step 1. Treat a pair of BECs as a TEC. Step 2. Prove that TEC becomes balanced after you apply parallel and serial stuff. Step 3. Prove that TEC becomes edge-heavy after you apply parallel and serial stuff. Step 4. Prove that edge-heavy implies fast polarization. With those 4 steps, we can show that BEC enjoys mu less than 3.4 using finite field arithmetic. What will happen if we use GF8 will be of future work. Thank you for watching.